Hello everyone, my name is M Katritsis. I am a PhD student at the University of Cambridge, and today I am going to present to you dialogí, which is a text mining approach for the identification of DILI-related literature with automated concept extraction. So I think it would be useful to start with a short introduction to the challenge. Here we want to classify papers that are associated with unexpected drug-induced liver injury. In order to do that, we only have access to titles and abstracts. So during this work, there are no full texts considered. Throughout the presentation, I am going to talk about internal as well as external validation. Internal validation uses the release datasets. These datasets include about 14,000 papers, that all come from PubMed, and are equally split between a DILI positive and a DILI negative group. Then external validation is based on withheld datasets and was conducted in 2 rounds. During the first round, we gained access to 10,000 papers in a balanced dataset, and then the second round provided access to additional 2,000 papers, but the dataset was imbalanced. Now, with the introduction out of the way, I will briefly go through the contents of this presentation. I will first talk about the text preprocessing that we are doing, and this includes normalization as well as annotation. Talk about the 2 classifiers that we use, fast text as well as a neural network based one that we are building. Focus on the second one and explain how we are improving its classification performance by appending drug similarity metadata to it. Then talk about the hyperparameter optimization that we are doing, as well as how we conduct our cross-validation. Quickly go through the idea of Keydrag identification, and then finally summarize everything and talk about future perspectives. Before I move on, I want to point out that while we have internal validation results for all models, we only have external validation results for the first and the last model that we built. So now let's talk about text preprocessing and specifically normalization. And in our case, normalization is a 2-step process. During the first step, we want to make words comparable across texts. And to do this, we first merge titles and abstracts, we then segment sentences and words, and then finally we map each word to its base form in a process that is called lemmatization. During the second step, we want to filter out any uninformative lemmas. And we do this by first removing lemmas that are less than 3 characters long. We then filter out numbers, punctuation, as well as stop words. And then finally we do a part of speech filtering, where we only keep nouns, verbs, adjectives, and adverbs. This whole pipeline is run in Stanza, which is the Stanford NLP package in Python. Then the next stage of text preprocessing is concept annotation. And here we essentially want to extend the normalization that I just talked about to drugs and disease as well. To do this, we use a tool called PubDator Central that also has a public API that we are accessing. And PubDator provides annotations for drugs, diseases, as well as species, but most importantly, it normalizes both drugs and diseases to their respective mass identifiers. So what this means is that now we can go in text and we can replace those drugs and diseases by their IDs. Since we want to further normalize DILI-associated diseases, any of them that fall under the liver diseases mesh term are given the same tag. And so if we take a look here, we can see what the final preprocessed text looks like. A lot of words have been removed, all retained words have been lemmatized, and also drugs, diseases, as well as species have all been annotated. So this is the final preprocessed text that is then passed along to the classifier. So we are now in a position to briefly talk about the first classifier that we used, and this is fast text. And in this case, we are using fast text to learn word embeddings in a supervised manner. And the way it works, in order to calculate text embeddings, it simply averages word embeddings. However, this is an issue here, because we expect what sequences matter. So in order to overcome this problem, we built our model to use n-grams, and more specifically, the classifier that we use here was built with trigrams. Now this is a choice that is made for us during fast text automatic hyperparameter optimization, and this also optimizes other aspects of the model, like the dimensionality of the word embeddings that it is using. So with this out of the way, we can now focus on the results that we get during internal and external validation. And we see here that this model performs essentially identically during internal validation and the first round of external validation, with matching F1 scores and accuracies. And we have to keep in mind that during both of those rounds of validation, we are dealing with a balanced dataset. And so as we move to the second round of external validation, where the dataset used is imbalanced, we see a big drop in precision that in turn affects the F1 score and the accuracy that are lower in this case. And this can effectively be traced back to the fact that we are dealing with a linear classifier. And so if we want to improve our classification performance, we will probably have to move to a more complicated model. With this in mind then, we move on and define our own neural network classifier. And here we again have an embedding layer to learn word embeddings in a supervised way. However, this is followed by a bidirectional long short-term memory layer to predict paper text vectors. And when I'm talking about paper vectors, these are the vectors that are passed along to the final classification layers. In this case then, the paper vector is the same thing as the text vector, and I am stressing this here because this is not going to be the case anymore when we augment the model later on. We then have our classification layer that consists of a hidden tense layer and a sigmoid output layer. And finally, when it comes to training, we use binary cross entropy as our loss function, the Adam optimizer, and we also define dropout rates in both our bidirectional LSTM and hidden tense layers as a regularization step. So if we now take a look at the internal validation results that we have for this model and compare them to the fasttext model, we see that we get a lower equal value. However, the precision is higher, and these two balance out so that the two models are comparable in terms of F1 scores and accuracies. And the main difference between those two models comes from the fact that fasttext is also taking into account subword level information, and this is something we have not included in our model. So we are definitely looking into potentially expanding our model in order to include this kind of information as well in the future. For now though, we are expanding our model by adding drug similarity metadata. And the idea behind this is to append prior knowledge that can guide our classification process. Previously, when I was talking about the normalization steps that we are taking, I specifically mentioned normalization being done on DILI-associated diseases. And so we want to do something similar with drugs by taking into account the similarity between them. This can be done by focusing on the proteins that each drug targets. And this is a three-step process. We first need to learn target protein embeddings. We then calculate drug embeddings by averaging the embeddings of their protein targets. And then finally, we calculate paper drug vectors by averaging the embeddings of the drugs that show up in each paper. So now I'm going to focus on each step separately and go into details. And the first step is building our protein-protein interaction network. Here we start with drug bank in order to get a list of target proteins for each drug. And at this step we do not differentiate between proteins that show pharmacological action or not. Instead, we acquire proteins that each drug binds to. Then as we collect all those proteins together, we use string in order to acquire all the direct protein-protein interactions between them. Finally, we are in a position to create our weighted network. And this network includes nodes that are target proteins, edges that encode all the functional interactions between them, and we also use string interaction scores to weigh those edges. During the next step then, we want to utilize the weighted network that we just created in order to learn protein embeddings. And the reason we want to do that is because this is a very natural way of incorporating this additional drug similarity information into our neural model that is already using text embeddings for classification. An elegant way of approaching this is to use Node2Vec. A Node2Vec starts with generating random walks on the graph. It then treats nodes as words and random walks as text, and so it can simply apply Word2Vec to learn those node embeddings, and in this case, nodes are proteins. The issue here, however, is that by including Node2Vec, we also introduce complexity to our model. And this complexity is directly associated to the sampling strategy that is used by Node2Vec. So Node2Vec is using a second-order bias random walk to explore the graph around the node. There is a return parameter that affects the likelihood of immediately revisiting a node, and then we also have an in-out parameter but is tuning how far away we walk from a node. So then, by changing the bias that we introduce in the random walk, we in turn affect the similarity features learned for our proteins and for our drugs. And as a result, this can affect the performance of our classifier. I am not going to focus on that, however. Instead, I am going to explain to you how we augment the model by adding this new information to it. Here, it is important to point out that drag embeddings are learned completely independently from text embeddings. And before we can append this extra information to our model, we need to calculate a drag vector for each paper by averaging the embeddings of all its in-text drags. Finally, we can calculate the final paper vector by concatenation of the text and drag vectors. And this, again, is the vector that is passed along to the final classification layer. So let's now talk about the final results that we get, and we are first going to focus on the internal validation results, where we see that the augmented neural model gets the highest recall value of all the other models, and the same precision as a fast text model, and as a result it outperforms all of them, both in terms of F1 score and accuracy. Moving on to the external dataset, and this is for the second round of validation, where the imbalanced dataset is used, and we see that compared to fast text, the augmented model gets the same recall value but a higher precision, and as a result both the F1 score and accuracy are higher. So now let's go through hyperparameter optimization, and I am going to first look at the drag embeddings, and as I have already mentioned, those drag embeddings are learned independently from our text embeddings. However, during optimization we want to optimize everything together. So in this case, we optimize the dimension of those protein embeddings, and we also optimize the length and number of random walks, as well as the bias that is introduced in them. And those last 2 points are associated with node spec, so they are particularly important because they tune the similarity features that we learn for our proteins and in turn for our drugs. Then we also optimize parameters that are associated with our primary neural network model, and these are the dimension of the word embeddings, the units and dropout rates of our LSTM and dense layer, and finally the learning rate of our model. And lastly, about the internal validation that we do. For that we use a 2000 sample holdout validation dataset, and then the remaining 12,000 papers are used in a threefold cross-validation during model training. Then the last aspect of this work has to do with the Keydrag Extraction step that we do. Here we want to associate its DILI-positive paper with the drag that it refers to. And in order to do that, we use a rule-based extraction system. During the first step, we take a look at the title, and if there is only one drag mentioned there, then this is the drag that we extract. If this is not the case, we then take a look at the abstract. Again, if we only have one drag in the abstract, then this is going to be selected as our key drag. If we have more than one drags, then we also look for a DILI-related disease term. We then acquire a grammar dependency graph using stanza, and the premise here is that the key drag is going to be the one in closer proximity to that DILI-related disease term. We calculate proximity between key drag and disease term pairs using shortest paths. Lastly, if neither is true, we simply extract all drags that are mentioned in text and associate them with it. So now I am going to summarize everything and also focus on future work. First of all, at the very beginning of this presentation, I introduced a text preprocessing pipeline that is not only able to normalize text, but also concepts, with those concepts being drugs, diseases, and species. I then introduced a framework that is able to quantify drug similarity, but also encode this additional information in such a way that we can naturally introduce it to our neural network classifier. We then showed that by augmenting this classifier so that it utilizes both text and drag embeddings, we get improved performance. And then finally, I briefly talked about our Keydrag Extraction step that is trying to link DILI-positive papers with the drags that they are referring to. When it comes to future work, the obvious next step would be to expand our protein-protein interaction network with additional metadata. And such information could be adverse effects, so that we are dealing with a heterogeneous network and then we can learn drag embeddings. on that expanded network. We could also move in the other direction, and by that I mean that we could learn drag embeddings in a supervised manner. And if we do that, we could then directly use those embeddings for DILI prediction. Then, when the prediction score is close to the cutoff value of 50%, we could rely on full text instead, and so selectively download full text and run the same pipeline on them. And finally, we are thinking about creating an online platform that provides easy access to the tool and its predictions. And with that, this is all I had for you today. I will be happy to hear your comments and answer your questions during the Q&A session. Thank you very much.